title, Fundamentals of Analysis of Algorithm Efficiency. Fundamentals. Okay? A lot of concepts we need to learn and some methods we need to use, okay, in this lecture. The first unit, analysis of algorithms. The overview. So let's look at the overview of analysis of algorithms. So what is the analysis of algorithms? So what are the main things we need to study here after we get a solution? We need to estimate amount of resources to be used. Now, you want to evaluate if your algorithm is efficient or not. Okay? Yeah. Otherwise, you don't know it. Okay? Yeah. What kind of resource? The primary resource, running time. Running time, primary, okay? Most important resource. Okay? But there is a secondary resource, memory space. Okay? Less important than the running time, but still it's a, important factor. We need to consider it. Memory space. How much space do you use in your algorithm? Okay? Yeah. Sometimes people may argue because right now the memory space becomes cheaper and cheaper, right? Per unit cost becomes cheaper and cheaper. Okay? So why it is so important? Actually, it is important. Why? So think about this. To run your program needs to be loaded into the memory, right? So it takes the memory space to run your program. And usually, a computer runs multiple programs in the memory, right? So several programs running in the memory. So all of them need a lot of space. Right? So if your program uses too much space, the performance will be slowed down. Okay? Yeah, run out of space, you have to wait until the space is available. Then you can go to the next step. Every step, you will have shortage of the space. You have to wait until the space is released. Then you can go to the next step. For that reason, memory space will impact running time. So it will waste too much space. Your program will be very slow. Right? So for that reason, we need to reduce the amount of space used. Okay? Yeah. But in our analysis, most of our time we put here, but sometimes we try to look at that problem. Okay? Yeah. All right. Methods used to study analysis. Okay. Yeah. Two methods, theoretical and empirical. Okay? Theoretical, yeah, we use math, to give us conclusions. So we do a lot of math computation. Okay? Yeah. Empirical, we need to do experiments. We need to write programs. So we run our programs and see the results. For example, when you count number comparisons, in our program we can also count number comparisons. Okay? So we can see how many comparisons do we need to run this program. Right? So that kind of thing, empirical. So write a program to do experiments. Okay. All right, so at this point, I can give you a little information about our project, programming project number 1. Our programming project number 1, you need to write a program to do experiments, to compare performance of two programs. Okay? One use a good algorithm, another use a, bad algorithm. Okay? So you run each one, then you compare. Okay? Yeah. So that's our first programming project. Yeah. So I will give you more and more information about that project. Okay. All right. Yeah. So, but most of the time we will spend for this part. We will do a lot of mathematical work. All right. A lot of mathematical work. All right. Main concepts in analysis. Efficiency of algorithms. We use this term a lot. Efficiency of algorithms. Okay. Regarding efficiency, there are two types. First, time efficiency. Yeah. Our primary factor. Sometimes we also call time complexity. Yeah. The second one, space efficiency. Okay? Space complexity. Yeah. So that's the basic concepts. Yeah. Oh, here for the space efficiency, I need to explain a little more the meaning, exact meaning of space efficiency. Okay? Exact meaning. The amount of memory units you required by the algorithm in addition to. Okay? This in addition to is important. Okay? The space needed for its input and output. Okay? So mainly we look at that in the addition, that part. So what is that part? Okay? Given an array, that's your input, right? This array uses certain amount of space, okay? But we do not count that. Because every algorithm, you must use that much space, right? We only count extra space we need to use. We do not count the space that everyone must use. So input, output, everyone needs to use that space, right? Input, output. But sometimes your algorithm needs to consume a lot of extra space. So we look at the extra part of the space. Right? Yeah. So that's the space efficiency. Then another question regarding the input size. What do you mean input size? Right? Here, we have an idea. At this point, we solved 4 problems. So we have some idea about input size. Okay. First, the meaning we're familiar with, number of data items in the input. Number of elements in your array. Okay. Number of data items. Yeah. That is the most commonly used meaning. Okay. But there is another meaning. We haven't seen that kind of problem, but we will see, quickly. Yeah. So based on the size, we have an idea. So usually, the larger the size, the harder the problem. Remember our polynomial problem. The larger the size, the harder the problem. Okay? If we reduce the size, we can make the problem easier. Yeah. So that is a simple fact. All right. Another type of input size, the magnitude of the number. Magnitude. So here, we'll only give one number. But when that number is large, the magnitude is large, then the problem is harder. Only one number. One number means the size is 1, right? The size is 1. But, the size, yeah, because the size, the meaning is different. Okay? If we use this understanding, the size is 1. Right? But the problem, this situation, we cannot use this meaning. Okay? We use the magnitude of the number as the size. What's that? Let me give you a simple example. Okay. Sometime we have that situation. Example, checking primality of a positive integer n. Primality, prime or not. Given a positive integer, you need to check, is this number a prime or not? Okay? One number, okay? But we know if this number is very large, checking extremely hard. Checking prime number extremely hard. Okay. Do you know a little bit about that? Checking primality. Checking primality really hard. Okay? Do you know, yeah, there is an encryption algorithm called RSA. RSA, encryption algorithm, is based on this fact. RSA. Currently, our internet encryption using the RSA, 128-bit encryption, right? We use 128 encryption. Okay? So that algorithm is based on this fact. Checking primality, not just checking, you need to decompose a large number. Decompose large number. Given a number with hundreds of digits, how can you decompose it as a product of two smaller numbers? That computation is very hard. Very hard. Very hard means takes a lot of time. Takes a lot of time, that means people, if you want to break it, if you want to even use supercomputer to break it, it takes a long time. So if it takes a long time, then it is safe for us, right? If we use that algorithm to encrypt our internet data, we feel safe. If other people can break it easily, we do not feel safe, right? So that's why, so currently, you may have heard of quantum computer, right? So those people claim, so if the quantum computers can be built, then because it will be much faster, it will break this algorithm easily, just in a few seconds. But they just claim it. We haven't seen it, so we don't believe it until we see it. Okay? Yeah. So here, the whole story just tells you, in this situation, the magnitude equivalent to the size of the problem. Size. Okay? Yeah. All right. How to measure running time? Yeah. How to measure running time? Yeah. Basic question. Yeah. Need a scientific method to measure the running time. We want some relatively easy way, and also it's a stable way. Not just easy, also stable. Okay? Because you cannot use a clock to measure the response time, right? Because it's not stable. Right? You use a clock, for different computer, different hardware, software, your response time will be different. So that method is not a good one. So we want a stable one. So no matter where you run it, so you go anywhere, you get the same measure. So that's a stable one. Okay? All right. How to get a stable running time? Yeah, our next question. Yeah. It does not rely on the hardware, computers. Yeah? Yeah. So we don't worry. So I have a very slow computer, 10 years old computer, don't worry. So our measure does not rely on it. Okay? Yeah. It does not rely on the quality of the programs. Yeah. Quality. Yeah. We know some people can write much better quality programs than the others. Yeah. So we don't worry about that. Okay? So because our measure does not rely on that factor. Okay? Or we try to remove those factors. So we can compare in a fair playground. Yeah. All right. Main approach we use. Use the basic operations. So we define this concept. Basic operations we used in our algorithm. Yeah. So what is the basic operation? Yeah. The meaning is the operation contributing the most to the total running time. Contributing the most. Yeah. For example, in our polynomial problem, multiplication contributes the most, much more than addition. So we treat multiplication as the basic operation, not addition. Okay? Not addition. In this sense, okay? In this context, in our algorithm efficiency context, we treat multiplication as the basic operation. Okay? Yeah. Count the number of basic operations used in the algorithm. That's our main approach. We count number of basic operations. Okay? That number, you can see it does not rely on your computer, hardware, and your program quality. See? Yeah. Okay. So that's the basic things. All right. Next, we need to look at the formula. Okay. Connect basic operations to running time. There is a close connection, but we want to look at what is the connection between these two concepts. Okay. All right. First, we need to identify the basic operation in our algorithm. So usually it's not very hard. Yeah. So we can figure out. Okay. Usually, the most time-consuming operation in the algorithm's innermost loop. Yeah. Yeah. You write a pseudocode, so you have nested loops. Yeah. Innermost. That means you need to use this operation most of the time, right? Yeah. Most time-consuming. Yeah. So based on that, you can find your basic operation in your algorithm. Okay. All right. Examples. So let's look at our examples. In our problem 1, we know multiplication is the basic operation. Okay. Problem 2 and 3. Yeah. Problem 2 and 3. Oh. Yeah. Anyway, yeah. So I feel the number may not be, if the number is correct or not. Yeah. Yeah. I will double check that. Yeah. Yeah. So those two problems, the basic operations comparison. Okay? Yeah. All right.